question, I think. Right. So now we are going to go into a new subtopic. And this new subtopic is shearing stress. For composite material. Now, you have looked at composite material before, okay? So composite material is basically you have, this is a cross-sectional view. And you have over here, you have your Y and you have Z. And then we have a cross-section, right? And then this cross-section has, okay, and this is made of material 1. And this is made of material 2. Right? So if you were to recall bending moment for composite material, okay? So for bending moment, the normal stress will be equal to N, okay, mz over izz multiplied by y, right? And the izz will be equal to N with depth cube over 12 plus by N with, okay, I like to multiply by the depth, multiply by y bar more y bar squared. Okay. And this N for material number 1 is equal to Young's modulus of material number 1 divided by Young's modulus of material number 1 for using material number 1 as the reference material. And then the N for material number 2 is equal to E material number 2 divided by E of material number 1. Okay. Why is that? Because over here I specify that we use material number 1 as the reference material. Okay. So reference material means material number 1 is always at the denominator. If N of 1, you have to use Young's modulus of 1. N of 2, we have to use Young's modulus of 2. Okay. So in terms of shearing stress, it's very similar. Okay, so in shearing stress, right, the shear will be equal to Vy over Izz. Okay, and then we have a N, okay, with that Y bar, right, divided by thickness. And this term over here, as you can see, is for our Q. Okay, so we incorporate the N, okay, the N over here to the first moment of area. Okay, whereas in bending, you just need to put the N down here. So if we want to find stress of material number 1, is equal to N material number 1 mz over izz multiplied by y, and you want to find N for material number 2, use N for number 2 mz over izz multiplied by y. Okay. Likewise for this. Okay, so if you want to find the shear stress of material number 1, you have By over Izz, again held constant, and for number 1, omega r width, depth y bar divided by thickness. Okay, and for material number 2, you have Vy over Izz, and for material number 2, with that y bar over thickness. Now, we don't divide by the thickness is just constant. Okay, you don't include the n again. If you put the n down here, because you say, Eugene, isn't it the thickness have to change? If you happen to put another n down here, what will happen? You cancel out the n's, right? The coefficient that you just cancel, and that's wrong. Okay, we don't do that at all. Okay, so now I'm going to work on an example. Okay, as I said, it's not difficult at all. Okay, but I'm going to work on an example. Okay, to look at shearing stress of a thin wall section. And if you go to Avenue to Learn, I could not remember, did I post this? I think I did. Hold on. I'm checking now. No, I did not. Hold on. Week number 9. Okay, week number 10. I'm going to, if you all were to go to Avenue to Learn, okay, I'm glad I checked. Yeah, I did not post it yet. Okay, if you go to Avenue to Learn, okay, you will have this examples. Okay, please try to access it. Okay, if you have problem getting to it, let me know. Okay, so we are going to deal with the first example over here. Okay, so this is example number 1. And I'm going to get the image. Right. So it states that a steel bar and an aluminum bar are bonded together as shown to form a composite material. Okay. Knowing that the vertical shear of the beam is at 4 kilopounds, okay, so we have Vy, which is equal to 4,000 pound force. And also given to us the Young's modulus of steel. Okay, so also given to us the Young's modulus of steel is equal to 29 times 10 to the power 6 psi. And the Young's modulus of aluminum, which is equal to 10.6 times by 10 to the power 6 psi. Okay. So we were asked to determine the average stress at the bonded surface. Okay. And then we are also asked to determine the maximum shearing stress in the beam. Okay, so we're gonna do this example. Okay, so what I'm going to do is we're going to pick a reference material. Okay, so for this case, I'm going to select. We're going to select steel as the reference material. Okay. Now, before we go into selecting steel for the reference material, we know that the shearing stress is equal to Vy over Izz. Okay. And then we have N, width, depth, Y bar divided by thickness. Okay. So what we know is we know that Vy is equal to 4 times 10 to the power 3, okay, pounds. We have not a clue what is our Izz. We don't know what is our N yet. Okay. The thickness we know. Thickness, regardless whether it's aluminum or steel, we know that this is equal to 1.5 inches. Okay, so the thickness we know. Okay, and the standard width, okay, the width is also equal to 1.5 inches. Because if we were to sketch the shear flow, okay, we know that over here, this is our thickness. Okay, so those are the our other information that we know. Okay, so now we are going to look at, we are going to determine Izz. Okay, we're going to determine Izz. And before we can determine Izz, okay, we have to firstly find the position of the geometric centroid. Because it's a sandwich material, you cannot say that, okay, the centroid is 1.5 inches from the top. Does not work like that now. Okay. So what we're going to do now is we are going to use steel. Okay, we're going to use steel as the what? Reference material. Okay, we're going to use steel as a reference material. So we know that the N of steel is equal to Young's modulus of steel divided by Young's modulus of steel. This will give us 1. Okay. And then we know the N of aluminum is Young's modulus of aluminum divided by Young's modulus of steel. This will be equal to 10.6 divided by 29. Okay, so 10.6. Okay. So this is equal to 53 over 145. Right properly. Okay. So next, after specifying this, okay, we are going to take the top as the datum. Okay, so the top is the datum. So we are going to have our section. Okay, so we have the section